and digestive system. How many? 9 questions. And respiration, 9 questions will be 25. Yeah, 25. Okay. I will make questions for these. And for these questions, I have no idea. So I suggested 11A to read the book carefully, at least once. I'll share the book with you if you don't have the pages. Okay, let's study the respiratory system then from the beginning. And today we have done unit test with 11A. You can do that too. So it will be like a practice. Okay, so let's start respiratory system then. Okay, let's stop this. Okay. At the beginning of this chapter, there is a definition. There are 2 definitions in the book. In general, with respiration, we mean like something like exchange of gases, gas exchange. Here in the book, like there are 2. Did I write them here? Yeah, there are 2 respirations. One of them is external. Okay, this one, external respiration. This means gas exchange between respiratory organs and the blood. Like, let's say this is our body. Right. This is us. Oxygen entering, CO2 external, oxygen coming in into the lung, to the blood, it's going out. This is external respiration. To the book, internal respiration is the one inside the cells. What's happening? Down sugar into carbon dioxide, water, and energy. Carbon dioxide is produced. So, cellular breaking down of food, let's say glucose, to release energy. This process uses or consumes oxygen and produces. Because of this, we have to breathe in oxygen and we have to breathe out this produced CO2, right? And in the chapter, there is also breathing. This is a physical process, like moving air into the lungs, breathing in, moving air out of the lungs, breathing, inspiring, expiring. Okay, we'll look at that. That's one of the important things, I think. How do we breathe in and out? So the introduction is like this. The meaning of respiration in general, and then internal. You should check this from the book too. Internal, inside the cells. External, from outside into the body, from inside to outside. Okay, the other organisms is not important for this time, not in the book, I think. Every living organism does something like our activity to take in oxygen and to remove CO2, even unicellular organisms. And then like worms, then maybe insects, then this is fish, and this is the other vertebrates. Okay, this human respiratory system is important. You need to know the names of the parts. Okay, let's look at this one. This is more complete with a zombie human. So this is better. There is the nose here and also mouth here. So we can use these 2 openings, both of them okay for breathing. But the book says breathing with the nose is better because the nose like kind of filters some dust, right? And also like kills some of the microbes entering because of the secretions. It also makes the air warmer and more moist. Okay, there is filtering, killing some microbes, warming the air, and then making the air more moist. So it is better for the lungs. Here it doesn't make much difference because the air is already warm, already moist. At least there is this filtering activity. Okay, after that, the both ways combine here in the pharynx. Pharynx is back of the mouth. Okay, and then we go down, there is larynx here, voice box. Inside here, there are two cords. When air passes, we make sound. Then trachea is important. Trachea, this tube, trachea. Trachea has some adaptations, like it has ciliated epithelia. And it has mucus secreting cells. It has mucus, a lot of mucus, and it has cartilage rings. Cartilage rings. We are going to look at them. So this is trachea, special one, and then branches into two bronchi, bronchus, bronchi. Bronchus, one of them, bronchi, plural. One bronchus enters the left lung. This is left, and one bronchus enters the right lung. And then inside it branches again into smaller tubes, bronchioles. Okay, trachea and bronchi are similar. Both of them have the cartilage rings to keep them open all the time. But the bronchioles are very tiny. They don't have any special thing. And at the end of bronchioles, not shown here, but at the end of bronchioles, there are alveoli. Alveoli. Or alveolus. Okay, so this is the path to alveolus. You need to know the path, like nose, pharynx, larynx, trachea, bronchi, bronchioles, and then alveoli. Let's look at this one here. This is more clear. Like this, larynx is here, trachea, bronchus, bronchiole, and then alveoli. Okay, there are some other supportive things. There are ribs. Okay, let's clear these. There are bones. Bones, are they named? Nope. These bones, ribs, or costa. Okay, there are two names. Latin name is costa. These are forming a cage and protecting, kind of. They also kind of help in breathing. There is this muscle, diaphragm. This is the breathing muscle. This is the main one, most important one for breathing. This separates abdomen from thorax. Okay, thorax is upper part, abdomen is lower part. The two lungs, they are not equal. A left lung is smaller because there is heart here. What else? Between the rib bones, there are muscles. There are muscles here called intercostal muscles. I think that's all. And one more thing. You see the membrane for the lungs. Okay, this is left lung. There is a double membrane, right? You see this double membrane. These membranes are called pleural membranes. And between them there is fluid. Between them there is fluid here to reduce friction. Like when we are breathing in and out, Lungs are becoming larger and smaller, larger and smaller. So they are touching the muscles, they are touching the heart. There should be no friction between them. For this reason, our lungs are inside this fluid. Just like the heart. Heart is also like that. Heart is here, let's say. There is a membrane outside, and the heart is inside fluid, pericardial fluid. Okay, then anything else? There are muscles too, like in the trachea and in the bronchioles. There are smooth muscles, automatic, right? These are to make the trachea narrower and larger. Sometimes when we are coughing, let's say, we make them narrow, so we push the air out. This becomes problems in asthmatic people. When a patient is having asthma crisis, these muscles contract and make the trachea and other tubes very narrow, so the person may not breathe because of that. And solution is inhaler. Inhaler. When they press that inhaler into the body, inhaler relaxes the muscles so they can breathe again. That's for asthma. Okay, nose is filtering, cleaning, killing some microbes. Not necessary, not necessary. Larynx is producing sound. This one. Trachea has, okay, three things. Rings, cartilage rings to keep it open all the time. Ciliated cells to push, wait, here. Ciliated cells to move mucus to throat, up, like from lungs, away from the lungs towards the throat. Why mucus? Because mucus is sticky, so it traps dust and bacteria. The air we breathe contains many dusts, bacteria, viruses, many things. So when the air is going in, we have to remove the mucus. That is done by ciliated cells. And the cells producing mucus, they are called goblet cells. Goblet cells produce mucus. Like here in this diagram, we see part of the trachea. This is inside trachea. So air is moving in and out. Here, ciliated cells, cilia are here. And these are goblet cells producing mucus. This is mucus. And this is trapped dust, like that. So they are going up slowly. If the person is smoking, these cilia, they don't work well. So mucus doesn't go up, mucus goes down then towards the lungs. And then the person has to cough a lot to remove the mucus. That's why smokers cough a lot, because mucus is going down, kind of, to push it back. This is a little bit more detailed. Then two bronchi, like trachea becomes two bronchi, and this one is esophagus. Has nothing to do with respiration. This is for food. Food is here, air is here. Bronchioles, many. Okay. Then at the end of bronchioles, we have alveoli. Alveoli are our gas exchange surface. So here, oxygen really enters our body. Like oxygen is inside alveoli. Blood capillaries are here. We are going to see better pictures. So oxygen enters our blood here, from alveolus into blood. Like this. See the blood vessels, capillaries. So O2 is moving from here into blood. CO2 is moving in here. There are two main adaptations of alveoli. Since we are doing diffusion, like oxygen and CO2, they are diffusing to get enough oxygen and to remove all of the CO2. we need high rate of diffusion. One of the key things for diffusion is the surface area. So in the lungs, in the alveoli, surface area is like really large. For an average person, total surface is like, they say this much, 140 meters square. Total surface of lungs, actually so big. Because of this, like instead of having alveolus like this, just like a balloon, we have many smaller ones like this. This volume is same, like when you have option 1, let's say, instead of option 2, when you have this one, volume is same, but the surface area is like 4 times bigger. If you do the mathematics, right? Instead of having 2, we have 1, so we have like 4 times larger surface. If you have smaller ones inside here, then it becomes even more, not 4 times. Maybe adaptation is really large surface area. Second one is the distance is very thin. Like from alveolus into blood, the distance is very short. Like here, this is alveolus. So this is single cell wall, and this is also single cell. So oxygen passes from 2 cells and it is in the blood. Okay, so like both of them, alveolus wall and capillary wall, they are 1 cell thick. So the minimum distance. This one is oxygen, this one is CO2. All gas exchange surfaces, not only, they should have large surface area. They should be moist. This is not important for you, I think. Don't worry about this. Thin walls, well ventilated, meaning oxygen, more oxygen must be coming. This is diffusion. Concentration gradient is important. If you want oxygen to go like this, here oxygen should be small, here oxygen should be big in concentration, right? We continuously breathe to keep oxygen high here, and blood is moving to keep oxygen low here. And for CO2, the opposite. Blood is coming and bringing more CO2, and here we are breathing out to remove CO2. So we keep CO2 low here and then high in the blood. So diffusion works fast. Okay, what else? Now the ribs, we come to breathing. Ribs are like this. They form the rib cage for protection. And then between them, there are intercostal muscles. There are 2 sets. One set outside, like this, and one set inside. How can I show that? Like one set inside here, and another set outside. They do different things. The ones outside, okay, let me show you the inside one first. Inside ones are called internal intercostal muscles. So they are inside the rib cage. Okay. And when they contract, they pull the ribs inside. So our chest volume becomes smaller like this. When we are coughing, we use them. Like when we cough, like, like your chest volume is decreasing because of these mostly. And the ones outside, they are called external intercostal muscles. When they contract, our ribs go outside. So this happens. Like when you're taking a deep breath, you pull the ribs out. Okay, so we use them when we are taking a deep breath or when we are forcing air out. You need to know which one do we use when we are breathing in, which one do we use when we are breathing out. Okay, the most important muscle here is diaphragm. Original shape is like this, parachute shape. or dome shape, like the one on top of the mosques, dome shape. This is the original, relaxed. When it contracts, it becomes like this. So when it is contracting, it goes down. When it is relaxing, it goes up. Think about it here. When it contracts, it goes down. So our volume here becomes larger. Okay, diaphragm is a sheet of muscle. The difference here, the breathing mechanism. Like the diaphragm, this person is breathing in. So the diaphragm is going out. Look at this arrow, going up, going down, sorry, not out. And then when we are breathing out, exhaling, diaphragm is moving up. So you should remember this. Where is it? Oh, it looks a lot here, but it's actually could be simpler. Look, when we are breathing in, or when we are inhaling, or there's another word, inspiring, and here exhaling, breathing out, expiring. You may see one of these three, all of them are used. Okay, let's say we are breathing in, okay? The idea is about pressures. If you want to breathe in, if you want air to go into your lungs, the pressure here, the pressure of lungs, let's say, should be smaller than the pressure of atmosphere, atmospheric pressure. It's all about pressure. If lung pressure is smaller, air goes in. If lung pressure is larger than atmospheric pressure, air goes out. Atmospheric pressure doesn't change much, but we can control the lung pressure with this formula, P1 times V1 equal to P2 volume 2, right? Let's say you want to breathe in, you have to make the pressure smaller. To make the pressure smaller, according to this formula, if pressure is going to be smaller, volume should be larger, right? So if you want to breathe in, you have to increase the volume of the lungs. How do we do that? Most important one, diaphragm should be going down, and also your ribs can go outward a little bit. Most of them, that's why, like when you look at somebody sleep, you can just look at the abdomen part. If the tummy is going up and down, then the person is breathing. But breathing is in the lungs. Why the tummy is going up and down? That's because like diaphragm is pushing. When you are breathing in, diaphragm pushes the stomach and intestine, so they go out a little bit here. Okay, let's look at this what's the table, say. To breathe in outside, get the logic in your, connected to volume. Like when the external ones contract, they pull the ribs, volume increases. So ribs are moving up and out, volume increasing. Then diaphragm contracts. Most of the time questions are about this. Diaphragm contracts and flattens, like this one. This becomes this, more flat. When these two happen, when number one and number two happens, volume of the thorax, chest, increases, and the pressure inside the thorax decreases. This is P1, V1. And then atmospheric pressure is constant, lung pressure is decreasing, so there is a difference. Because of this difference, air moves into the lungs, and then lungs inflate, lungs become larger. This one is opposite, just opposite. It looks like this. This is the lung model. This is diaphragm. right? When you pull this down, when you are pulling this down, you are increasing the volume. When you are pulling this down here, volume is increasing, pressure is decreasing. Because of this difference, air is moving in to the balloons, and the balloons inflate, become larger. But if you move it up, or if you just leave it, it goes up, volume decreases, pressure increases, then the air goes out, escapes. Just like this, same mechanism. Here we are just using diaphragm. If it is the real one, we also use this part. This part is also moving a little bit. Okay, this is the mechanism of breathing in and breathing out. Most likely you will get a question about this, at least one. This one, lung capacities, you have to memorize this graph. Okay, and usually there is, even in UN exams, I've seen one question about this. Not very complicated, just the same one is also in the book. Same names, like English names. So just study. Let's go over it once together. What do we have? Let's say this is a male, I think, because it's like 6 liters, meaning a large male, larger than average. If the total volume is 6 liters, we call it total lung capacity, this one, all of it, from 0, empty, to full, maximum, total. Makes sense, right? Total. Then we usually don't use all of these 6 liters. Like we don't normally breathe like maximum and then force to minimum. We don't do that. Even if we try to remove all of the air, we cannot remove some of it. If you are living, if you are not dead, this much life, this volume is called the residual volume. It's always there. You cannot remove it. The numbers are not important. Okay, the numbers are not important, but the names important. Numbers change from person to person. So residual can't be removed. Always there. Okay. The other, like not residual. Residual is here. The rest is called vital, like life, vital, like life capacity. If you are living, you are using this. Okay, I made these logical connections, so I remember like that. If you are living, you are using the vital capacity. This is your largest breath. This is like you are coughing, maybe pushing all of it out. Okay, vital. But normally, again, we don't take deep breath all the time. We breathe in a relaxed way. This one is called, where's the name? Tidal volume. Here, this one. Tidal, like in the oceans, there is tide. Water is moving up, water is moving down, right? What do we call that in Bahasa? Tide in the oceans, and then going down, rising, then going down. Like it here, we just take normal breath in, normal breath out. This is usually like half a liter. Okay. Let's say you are just relaxed, breathing normally now, and then you want to take a deep breath. So from here, you go up maximum. This is our inspiratory capacity. This one includes the tidal. Tidal is inside it. Okay, the arrow doesn't show it well, but it's until here. Okay. The only confusing thing, I think, here, there is inspiratory capacity. There is also inspiratory reserve volume. If you know the meaning of reserve, that's also clear. Reserve is like you don't normally use, but you may use if you want. Like you are storing, kind of. So if you want to take a deep breath, the extra is this. Okay? If you are just normally breathing, you don't use the reserve. And there is another reserve, the last one, expiratory reserve. Normally we can force it out, but we don't. You just do this when you are coughing or forcing air out. Okay. Okay, sorry about that. Okay, I think clear. You should just memorize these. There'll be questions like, for example, they can just ask, what is the name of the lung volume when a person is just normally breathing in and out? Answer is tidal volume. What is the name of the volume which always stays inside the lungs? Sometimes formula like total is equal to let's say vital, a simple one, plus residual, right? A simple formula like this, total, all of it, equal to residual plus vital. So question can be like this: total volume is equal to vital capacity plus what? Okay, so diagram is important. Sometimes they give it to you, and then that's easy, that's just mathematics. They give this to you with the numbers here, maybe different numbers, and then ask you to calculate, like, what is the, let's say, inspiratory reserve volume according to this graph. Just look at the numbers and carry on. Okay, then the complicated thing maybe for this chapter, the most complicated part, but not that complicated, don't worry. How do we transport oxygen and CO2? Like, this is the general plan. Let's see what is what. This is lungs. Okay, this yellow thing here is lungs, so alveolus, one alveolus. And there are capillaries here. And then there is the heart. So we have the pulmonary artery, pulmonary vein from circulatory system. We have aorta here. We have vena cava here. And then one of the tissues, can be any tissue, can be muscle, let's say muscle. Let's say bicep. Okay, not lungs, any other body tissue. Body tissue, not lungs. Can be brain, anywhere, but not lungs. Okay, let's say oxygen is coming. Okay, oxygen is coming. We are breathing in, oxygen is entering. It is in the alveolus. Then it diffuses into blood, right? Then blood transports it from lungs with pulmonary vein to the left atrium, to the left ventricle, to aorta, and then to tissues. Okay, if it is kidney, renal artery, and then kidney, renal vein, vena cava, right atrium, right ventricle, pulmonary artery. Carbon dioxide now is here. Oxygen is used there, oxygen is gone, CO2 comes in, and then CO2 goes out. There are questions about this, like this one. Let me show you the question. I think it's somewhere here. Let's check this. So CO2 is moving from left toe, from your foot, and until nose, right? It must pass through all of the following except which one? From your foot, right? Your foot, it enters a vein from the leg, and then joins vena cava. The first name I know, I don't know the other blood vessels, vena cava. Then it goes into right atrium, right ventricle, pulmonary artery, right? Pulmonary artery to the lungs, and then lungs. Here alveoli. Here CO2 diffuses. from artery, capillaries, and then lungs into alveoli. Now alveoli, bronchiole, bronchi or bronchus, one, trachea, larynx, pharynx, right? Then nose. So it goes like this. Now, which one is the answer then? Right atrium, right ventricle, we passed. Trachea, of course. Alveolus should be there. Pulmonary vein. We use pulmonary artery, not the vein. So question like this may come. Okay, this is about the path. It can also be for oxygen. Let's say you are breathing in, oxygen enters, then the other way. But the thing is, like, okay, oxygen, sorry, I'm going the wrong way. Oxygen enters the blood, but then how is it transported? Okay, here we say oxygen enters the blood, CO2 enters the blood, but then what happens? It's like this. The oxygen is transported by red blood cells, erythrocytes, mostly, as oxyhemoglobin. This is like 97% of the oxygen. If 100% oxygen enters your body, most of it, 97% of it, is transported as oxyhemoglobin, hemoglobin with oxygen. Oxyhemoglobin, this name is important. Hemoglobin plus oxygen, oxyhemoglobin. Here, let's see, do we have it? Yeah, here. Okay, let's look at this one. Don't look at this. Here, this is hemoglobin. One hemoglobin. It's made of 4 polypeptides. This is a protein. Hemoglobin is a protein, by the way. And this large protein is made of 4 units called polypeptides. Okay, 1, 2, 3, 4. Okay, and at the center of each polypeptide, there is one iron atom. Okay, and each iron atom can bind to one O2. So hemoglobin can carry 8 oxygen atoms or 4 oxygen molecules, 4 O2. Okay, when we say oxyhemoglobin, we mean this. Maybe we'll see it there. It's actually HbO8, actually, or HbO2 4 is better. Okay, so like this. What about the remaining 3%? Oh, I didn't write it there, but it's here. Nope, not here. Wait, don't worry, it should be somewhere here. CO2. Yeah, here. Okay, looks complicated, don't worry. Just look at this one. Left up. Okay, left upper corner. Alveolar space, alveolus. This is alveolus. Oxygen is there. Some oxygen, most of it, look at the arrow. This is 100. 97 is entering the red blood cell. This is just 3%. 97 enters the red blood cell, combines with hemoglobin, becomes oxyhemoglobin. The remaining 3%, it just dissolves in plasma. Okay, and then this goes to tissues, travels to the muscles, let's say. In the muscles, what happens? Oxyhemoglobin now dissociates, separates. Oxygen is free. It can just diffuse out. And the oxygen in the plasma, 3%, it also goes out. This looks like what to me? Yeah, here. Let's say there is a river. There's a river here. River. You are here at point A. You want to go to point B. You can just, if you are a good swimmer, you can just jump into the water and then swim to the other side and then come out. Right? You can do that. This is 3%. Just dissolves in the plasma and then goes. The other 97% does what? There is a boat for safe transportation. This is a boat. In the boat, there are seats, safe seats, okay? The person sits in one of the seats and then puts on the belt, safety belt, then goes there to the other side. When on the other side, gets off of the boat. What is the boat here? Or what is the man here?
Oxygen.
Man is oxygen, yeah. Boat is what?
Blood.
Blood is the river.
Red
Oh,
blood cell.
blood is the water.
Blood cell.
Yeah, red blood cell. Boat is the red blood cell. Seat is what? The seat, the chair.
Hemoglobin.
Hemoglobin, good. So oxygen, like the man sits on the chair and a safe. This is oxyhemoglobin then. Together, they go there. When they reach the destination, they separate. The hemoglobin always stays there. It doesn't go out. Okay, this is the transportation of oxygen. For CO2, things are a little bit more complicated. Okay, there are three possible ways. 10% is dissolved in plasma, according to our books. In other books, there are different numbers. There is 7%, others. But our new textbook says 10%. Okay. Minimum number is dissolved in plasma, just like men jumping in water. And they eat chair and then going like that. 30%. The combination is called hemoglobin plus CO2 combination is called carbamino hemoglobin. Not carboxyhemoglobin. Carbon monoxide. This is carboxyhemoglobin. Hemoglobin. You then carboxyhemoglobin. This is problematic. This means you are in danger. You're okay. Anyway, long story. So last one, plasma, not by red blood cells, by plasma again, as bicarbonate ions, HCO3. So plasma is transporting 10% as just as carbaminohemoglobin. And how about this? How does this happen? There are two-step reactions. There are two reactions, like two steps. First, inside the red blood cells, CO2 combines with water. Okay, CO2 enters the blood. CO2 enters the red blood cells. In the red blood cells, it combines with water with the help of this enzyme. This is also important. You need to remember carbonic anhydrase. And they make this carbonic acid. Okay, the first step. First step, make carbonic acid, and then don't wait, just continue. Change carbonic acid to hydrogen ion plus bicarbonate ion. And then bicarbonate can go travel safely. You may ask why we have to do this much. It's about pH. You know, it's about pH. There is something about pH. You cannot put too much CO2 into blood. CO2 CO2 is acidic, this will make pH will decrease. That's not a good thing. So there is this solution. This is kind of alkaline, balancing things. We have to know this equation. This is important. So in our tissues, in your muscles, let's say, when you are exercising, what happens? Let's go step by step one more time. CO2 enters the blood, diffuses, and then enters the red blood cells for this reaction to happen, because the enzyme is there. This enzyme is inside red blood cells. Then CO2 plus water becomes carbonic acid. Then carbonic acid becomes 2 ions. Then our bicarbonate ion goes out into plasma and then travels in the plasma. This looks like what? With the river example, say you are here, you want to go to the other side. You don't know how, you know how to swim, okay? But you are coming from work, coming from school, let's say. You are from school, you will go home. Okay, so you have the school uniform, but you want to swim. There is no space in the boat, maybe, or like that. You cannot swim with your school uniform. So there is the boat here to help you. In the boat, there is a man. Let's make it a fat man. There is this man. This is carbonic anhydrase. Okay, this is carbonic anhydrase. You jump into the boat. In the boat, there is a cabin, so you can change your clothes. You go into the cabin. You remove your uniforms. You put on swimsuit. You became like swimmer then. Okay, so you leave your school uniform here, and then you get this man gives you swimsuit. So swimming to the other side. When you come here again, opposite, you get into the boat. The man brings your school uniform here. So you give the swimsuit, you get the school uniform and go home by swimming in water, not in the boat. You are just using the boat to get your swimsuit, kind of. So this way looks like that to me, kind of. It's 60%, most of the CO2. Okay, there are questions. Even in my unit test, there was a question. Most of the CO2 is transported by the blood in which form? Options like this one, or carbaminohemoglobin or carboxyhemoglobin, or dissolved in plasma. It is 60%. I think definitely you'll get a question about oxygen and this, maybe 2 questions. If this is where enters red blood cells, let's say 90% enters red blood cells. Can you hear me?
Yes, sir. But I think your connection was bad before.
Okay, I think my connection is about Singapore. This is like summary. You can look at it, but numbers are different a little bit. Like 30 here, this is 60. So our book has different numbers. If you get numbers, you should stick to book's numbers.
Okay.
Okay, so you see chlorine is here again. Sorry, not this one. That was calcium. Sorry. No need. Don't pay attention to that. There are questions like this. Let's answer one of them.
Sorry, sir. The
Which of the
presentation.
following reactions
The presentation is gone.
Oh, you
Yes.
see.
You're
Okay,
not
let
screen sharing.
me. Maybe I should share. Yeah, now. Okay, fine. Sorry, coming. Can you see it now?
Yes,
No.
sir.
Wait. Can you see which of the following reactions or something else?
Yes, we see the questions.
Okay. Okay, fine. Fine. Then let's look at this. Which of the following reactions prevails like main reactions most in about this? Where are we? Are we in the lungs? Because there different things happen. Or are we in the other tissues? We need to know that. Because here it says alveolar capillaries, so we are in the lung. Oxygen entering blood, CO2 is going, right? Simply like that. Now let's look at the reactions. Hemoglobin is combining with oxygen, making oxyhemoglobin. This is lungs. Okay, this means oxygen is entering blood. Can you see?
Sorry, sir, your connection is quite bad, so we can really hear your voice clearly.
Oh, okay. What can I do? Let me restart, yeah. Restart the connection, and then maybe 1 minute. Let's give a break. Maybe I share the exam with you. You test, you look at the exam a little bit, 5 minutes maybe. Then we,
Okay.
hopefully it will be better.